Hi everyone. So I am Nahid. I am a machine learning engineer at Meraki, which is actually part of Cisco. So we call ourselves Cisco Meraki. Um, we uh, we actually, I think many people probably don't know, we actually sell video surveillance cameras, and as you can understand, that obviously has certain intelligent applications. So yeah, today I'm going to show you kind of some samples, a very few small subset of the work we do, and how well sort of the segment anything model works on fisheye images. Um, I guess, yeah, so it's a full line of my resume. I so I have been working there for quite a while, and yeah, so and I have 7+ years of hands-on machine learning experience, and I actually lurk in the Voxel 51 Slack channel quite a lot. You guys have been great content. Um, so I think probably a good number of the audience might be familiar with the segment anything model, but I'll give a brief intro in the beginning. So what is segment anything really? So it is a foundational model for image segmentation. And when we say foundational model, what we actually mean is it it is very good at doing whatever the task it is designed for in unseen images. So for example, since segment anything is designed for segmentation, so it is really good at zero shot segmentation. So for example, this is on the left, do you have an image, and on the right, I'm doing segmentation. I'll go into detail. They have few different modes of operation, but this is one mode of operation where you can see like it is basically segmenting even the tongue of the dog, so which is quite interesting. Um, so if so there are actually, as a user, you can use segment anything in three different ways, actually. So you can say that, hey, I want to sort of like segment everything in that image. So that is everything mode, which is the example you saw previously, that is everything mode. So everything in that scene, it segments. And the next is kind of like bounding box mode. So let's say you have a data set that is already bounding box annotated, and you want to run segmentation on it. So you can actually do bounding box based segmentation. So here I basically draw a bounding box around the dog, and it's quite interesting that you see that it can accurately segment only the dog, and note that it's actually not taking any other things from this scene, like part of the hat or like the bag, right? So it. That's actually really very good, right? Um, the third mode of operation is actually based on point. So in this example, you see that I put a point on the dog. It's just a dot, and the point can be in like any part of the object that you want to segment, and it does, based on one point, it actually does a pretty good segmentation, right? So I guess the interesting question for folks who are actually building and training the model is, um, from a design perspective, like how can we design a foundational model like this, right? So the authors mentioned, and the paper is actually very detailed, so you can look into it. There are three main components to this design principle. So the number one is, what are the tasks that we want to tackle in the model? What is the type of model architecture that can support this type of task? And what type of data we need to collect that can help train the model that can do these tasks, right? So those are the three key questions, and in a sense, they're kind of intertwined. So we'll go over that one by one. So let's say first, let's talk about tasks. So they kind of took the inspiration from a lot of language modeling work, and they defined their task as promptable task. So what prompt actually means in this case? I think if you are familiar with language model, you know that text is kind of the prompt there, right? In this work, actually, they expanded this concept of prompt to more items beyond text, essentially. So, so in their definition, prompt is bounding box, segmentation mask, points, and also text. So that on the diagram on the leftmost part, you can see that these type of prompts, they are feeding to the model architecture along with the image to get a valid mask. And if you think of, okay, these are the prompts, so they are essentially helping you kind of defining your pre-training objective for the model, right? And in a way that the 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 final segmentation model is eventually like very good at downstream segmentation task for unseen images, right? So in the previous this slide, you saw that, okay, we have this task and then we have this model. So I'll expand the model a little bit here. So when they say model, it's the segment anything model. There are three different model actually inside it. So the number one is like your image encoder, which is MAE pre-trained bit essentially. And I think they just made a few changes on, like if you search for MAE bit, like you'll find something on Hugging Face. I think they changed that in a sense that they updated they worked on a different image resolution. And yeah, so that is essentially the image encoder. And then they have a prompt encoder. So we talked about this point and box and mask. So they pass the point and box and text through the prompt encoder. And then both the output of the image encoder and the prompt encoder goes through the mask decoder, which that's also a transformer based model, but much more lighter weight than the image encoder itself. And the output of the mask decoder is essentially the masked output. And obviously, like at that end, once you have like multiple output, the last layer is basically deciding on which output is basically best to output you to the user, right? And the last piece of the puzzle, and if you read the paper, you'll really appreciate the amount of data work they did. So the last piece of the puzzle is, and I'm bringing this as the last because it's not really last, but this is kind of connected to where we go next. That is like how they sort of curated their data. So for them, like they thought of this, like if you think of the how when we typically make a foundational model, a lot of these models are based out of like we use scrape data from online and from like web scale data, right? But the problem they had this to solve with respect to segmentation is that there is no such like kind of like you can scrape images throughout the world, but they're not really segmented, right? So what they essentially did was they created their own data engine, and that engine it's sort of like dog fooding because the model they have they sort of like use that to curate their own data in like three phases. So first is like the typical phase you can think of, like you have like manual and like people assisted, and then model outputs you certain things. So that is, you can say that is a manual phase. Then once you have some, then you go into like semi-automatic phase, and then from there you go into fully automatic phase. So they use their own model architecture to annotate their own data set in like 3 different phases. And throughout this process, they collected about 11 million licensed and privacy preserving images, and they created like about 1 billion masks. And I think they released the data set also afterwards. So if you look at sort of like this, this is SA1B is their own curated data set. And then once they have the model, they checked the performance on 23 different, like completely unseen data set. And so this is basically the list of those 23 unseen data set. And some of them are probably kind of, you might be familiar, like Cityscape and ADK are probably pretty common among all of them. And so in terms of like actual numbers, so what they actually did was they compared SAM versus RITM. So I think when the SAM paper was published, RITM was the SOTA on segmentation. And among those 23 data sets, they saw, I think, like about, I guess, 17 of them are like, they are better than RITM. So these yellow lines means they're better. And like, you can see like how much they're better. And the blue lines, they're on the negative side. So for these data sets, it's worse than RITM, basically, right? So I guess like, so taking a step back from here, so one of the thing so I guess like the problem we are sort of like trying to solve is we have different types of cameras, and like your regular like 19:6, 19:6, 9:6 images are like the typical images you can think of, like straight and all, right? But we have another type of cameras. Those are, we call fisheye cameras. So they're a specific type of lens that are ultra wide lens, and it has like 180-degree like field of view, and the images are typically like panoramic or hemispherical, right? And I mean, there are different categories of fisheye images or lens, but the point is, this is an example that they do not look like your regular images, right? And you might ask, like, why is this type of images important? Why are they important? And it is actually pretty common in video surveillance type use cases, and also on self-driving use cases. So this particular example I have taken from Woodscape dataset, which is public. And I don't know if you noticed, they actually tested also, they tested Woodscape with respect to SAM. And you see that compared to RITM, it is actually worse on Woodscape. So I'm showing you Woodscape example, obviously, because there are customer images that I cannot show you, so that it's a good example to show, right? So you see that it is really important, like for us, like we as a video surveillance team, let's say we are interested in vehicle detection. So in this example, you see there's a car and there are like a bunch of these bikes and stuff, right? And there are some cars on this side also. So it is important that we kind of like detect this for our use cases. And I'll show you what happens here is, this is, so I go back, I'm showing you an example of what happens if I do go into the everything mode of segmentation. with a segmented anything model. So this is the original image and this is the segmented image. And this is it's very interesting that you'll see that it does pretty well in terms of segmenting it, but you see it sort of like misses this part of where there is a bunch of bicycles, something like that. And this is in everything mode. You are supposed to, it is supposed to segment everything, right? And then the next slide. Yeah. So this one is like, okay, so what happens if we go into the bounding box mode? Like what happens if I sort of like draw a bounding box here? So then the model will segment this part, right? And you see, this is a bit messed up, right? So it detects some part, but not like this, the other bike. It only kind of segments the top, but not the wheel and everything. And at least this we need, this bike at least we need, because based on the bounding box where I draw, like the bounding box covers the entirety of the bicycle, right? But the segmentation does not take that into account. So, and like I wanted to give you this example of like a good example of like um, where even in like fisheye images, like there are situations where if you do bounding box like in other parts, like it does pretty well. So for example, in this case, I draw a bounding box on the car, which is more like straight. You're kind of looking straight, and you see how I did not draw the bounding box entirely. I intentionally made it kind of a little less perfect bounding box, but the model was really good at detecting this part, like masking this part, right? For the sake of completeness, I wanted to show you this thing, that if I do points on these bicycles, which are kind of on the corner, it does pretty well. So so essentially, like in this example, and this is quite a common example on fisheye images, that if you go on the everything mode or bounding box mode, typically on the corner of those fisheye images, you kind of start to see bad performance, or like you start to lose those objects, right? So I guess like a lot of these neural network debugging like ends up to this question of like why. Um, so why does this happen? So you can, before answering that, you can ask me like why is this age of this fisheye camera matter? Like does it even matter, right? And in this example, you saw that in our case, it matters, yes, because we want to make sure like these vehicles and like if there is someone entering, like we don't miss that. It's critical for surveillance use cases. And um, okay, so once we know that okay, this is important, then I guess like the next question is okay, so why it is not working well around the edge? So it's an assumption. Like I'm pretty sure they probably did not have fisheye images on the training data set, and if you don't have that in your data set, you are probably not thinking of designing the model in a way that understands that age and curve, right? Um, so what can we like? How can we sort of like debug this, right? How can we try to answer this question? So this is what we did is try to visualize the attention layer, attention patch from the mask decoder, because if you remember, the output of the model is actually the output of the mask decoder. So we wanted to understand that this read-based model, is it understanding, is it looking into all the parts of the image uh, in the right way? So you can see, like on the left, I have the example I showed with respect to bounding box around the car, and the bounding box around some of the bicycles on the corner. And so these were the results as you saw earlier. And on the right side, this is the visualization of one of the attention head from the mask decoder. And this is probably a little bit, I made it more sort of like expanded, so it got a little bit of flattened. But you can kind of see that around the edge where the bicycles are, it's like more darker. So lighter color indicates like there is more attention in that part of images. So for example, here you can see like it's basically getting most attention on these lighter parts, and even the car is getting pretty good attention. And but the on the part where there is like bicycles, mostly around the edge, it's more darker, like very dark. You can see like um, around like when it is like sort of like more downish, still on the corner, but more on the downish, like it's dark, but not as dark as the part where there is bicycle. Yeah, so there is sort of a lack of attention from the attention patch of the mask decoder in that part. So I guess like, so then the question is like, what can like what can we take away from sort of this analysis is it Sam has room for improvements obviously on these type of lenses. And so what can we do about it? I think if you are an ML engineer, I guess like the first thing that comes into your mind is probably like fine tune it on sort of custom data set. That might help. There is like certain other techniques. For example, these fisheye images, sometimes they you can sort of, there's a process called dewarping. So you can, from this round shape, you can make them flattened. And once that is flattened, maybe after that, you apply your logic of masking there. And so once you apply there, that might help. That's like another step. So in that way, you might avoid the fine tuning out. But then like it also depends on at what stage you are applying the masking. So if you are applying the masking when you just have the image and before dewarping, then there is a strong case that you might need a fine tuning at that point. But if you are applying masking after dewarping, then it might not be needed. So that decision choice depends on how much computing resource you have for your specific use case. Like if everything is on like in a MacBook or somewhere in cloud, then you can probably do dewarping. But if you have a very ARM based, very small compute kind of thing, then you might not have the choice for developing it. That's another added computation. So yeah, so there are trade-offs on that. Yeah, and this is probably a good point to say thank you and open the floor for question.
Yeah, so it does look like we have a few questions if you want to pop over to the Q&A box.
Okay. Okay, I see the Q&A box, sorry. Yeah, so I think Abdo is asking, have we measured improvement in SAM performance? Yeah, with the dewarping algorithm, after dewarping algorithm. Yeah, so it not yet. That's if that answers. Yeah, and so Dimitrios is asking, is the attention output corresponding to the queries box? Yes. Do you have you, okay, so another question is Matan asking, have you used camera calibration to simply adjust the fisheye images, converting it? So yeah, so this is basically the same. Have we applied dewarping? No, not yet. Have you quantified the degradation impact related to the distance from the camera center or by any other creative measure? So yeah, so we so it's more, so we have seen this consistently that on the corner of the image, it is that's why I chose that example. So uh, it's on the corner of the image is basically more degraded. So generally the center of the image is like, it's really good. Corner is where it is like it's less than that. Yeah. So I guess like Sai is asking, I guess Sai's question is kind of on the same line of dewarping, I guess. Yeah, so we have not applied dewarping yet. I think James is asking, are open standards of meta scene information labeling? If so, which one you are? I'm not sure I understand the question, James. Like that, Christina is asking, are the fisheye images generated basically by traffic in front of the camera? Where okay, yeah. So there are obviously, I think the two main use cases I have seen is one is the surveillance videos, surveillance cameras, and also like self-driving car. Christina, if that answers your question. Uh, um, yeah, so I think Dimitros, your question is like why it does not work on sort of like more distorted images. Yeah, so I guess like we're kind of trying to find it essentially, but the visualization example you saw is sort of like the attention, the mask decoder attention is not really good on the corner of the images. So um, if you think of like how sort of the transformer network works is like when you have like if it is have if they have like less attention, so that means your score is kind of low, and before you get the classification or segmentation output in this case, then you are multiplying that with the lower number, so so that part is not getting sort of like classified, right? So these are processed as RGB. Yeah.